I'm going to be talking about analog computation, and depending on your background, some of this may be review for you. A little bit of background about me: I'm a philosopher of science, and I have several interests in trying to explain analog computation. So what I'm going to do in this talk, first I'll talk about some of my motivations, and then give a little bit of an outline of some of the important analog computers from the past, and then say a little bit about how I think we can go about trying to understand those analog computers for the purposes that I mentioned. So let me start off with my first motivation. Generally, we understand quite a bit about some types of computation. So in theoretical computer science, we know quite a bit about Turing computation, or theoretical computation, or what people sometimes call the theory of computation, involving Turing machines and other automata. Philosophers have also done some work in trying to come up with an account of when a particular physical system implements a given abstract automata, because that's not the kind of thing that the theory of computation really worries about. Another, in a sense, form of computation that is based on some of the theory of computation is regular digital computation. And this is the kind of thing that all of our phones and laptops are based on. And by digital computation here, I mean something pretty specific, which I can talk about later. But this is the kind of computation where we're representing numbers by their digits, usually in binary format, and a lot of work happens in computer engineering to figure out the right way to design circuits so that we can perform manipulations on numbers represented that way. So in this little diagram, I have a little example of how floating point numbers are represented in single precision, and then this is just a kind of very basic circuit diagram of how we would multiply two numbers that are represented that way. Now, analog computation is something that people have worried a little bit less about and haven't tried to characterize very carefully, in my opinion. This is from a recent article. The philosopher Gualtiero Piccinini has done a lot of work in philosophy trying to make sense of computation. And this is a quotation from this article that he and a physicist wrote, where he says, "Analog computation is often contrasted with digital computation, although it is a vaguer and more slippery concept. Roughly, abstract analog computers are systems whose function is to manipulate continuous variables, variables that can vary continuously over time and take any real values within certain intervals, specified by differential equations, so as to instantiate appropriate functional relationships between the variables." And that is a rough characterization, but he's right that it is somewhat vague and it is kind of slippery. So one of the things that I hope to do in my work is to make that a little bit more precise, and so that we can have an account of analog computation just for the sake of completion. If analog computation really is another kind of computation alongside Turing computation and digital computation and perhaps others, it would be good to just have a complete story of all the kinds of computation, and ultimately what it is that makes all of these things count as computation. What is it that they all have in common such that we should be, we're justified in calling them types of computation. Now, the other motivation that I have in trying to get clear about analog computation is that certain neuroscientists, particularly computational neuroscientists, often make claims like this. This is the neuroscientist Christoph Koch, and he starts his 1999 book on computational neuroscience. The first sentence on the first page is, "The brain computes." So I would kind of like to know, what could they possibly mean by this when they say the brain computes? And a little more soberly, these neuroscientists in their 2005 review article say, "Brains compute." That's also the first line of their first page in this article. Now, this is something that not all neuroscientists say so explicitly, but a lot of them do implicitly make commitments to. And so the picture is this: the brain is some kind of computer, right? And I think we have a pretty good idea of what we're talking about when we talk about brains. I think we know what this relationship is. It can be different things, and so we have to be careful about whether we mean the brain literally is a computer or something else. But over here, like I said before, we have a pretty good understanding of digital computers, of Turing computers, but we don't really have a good grasp on analog computation, at least in my opinion. So let me make clear what I'm not talking about, because it's very close to something in the neighborhood. As a lot of people know, computational simulations are absolutely ubiquitous in science. So here we have just 4 visualizations of some computer simulations. The first one on the left, that is of a tornado forming on the top left. On the top right, that's a picture of some binary stars. On the bottom left, that was a little image of some DNA molecules that are denaturing. And on the bottom right, this is just a 3D structural diagram of neurons. So all kinds of things in science are simulated computationally, and we can learn a lot about the phenomenon that we're studying by simulating them computationally. And there's a lot of interesting work there. I don't mean to say that that's not interesting. But saying that something can be simulated computationally does not at all imply that the thing that you're simulating literally performs computations. So computational simulations of galaxies or of tornadoes, of all kinds of phenomena, don't imply that tornadoes are computing or galaxies are computing, etc. But if you're saying that something is a computational explanation of some phenomenon, like what neuroscientists do, that does imply that the thing performs computations. The idea is that we're not just simulating brains, we're trying to figure out what computations the brain performs. So that's a much stronger claim. And so that's one of the claims that I'm interested in. What could that mean to say that some phenomenon literally performs computations? Okay, so now let me talk a little bit about some analog computers. For some people, this may be a bit of a review. So some of what I have here are old videos from the US Navy showing different kinds of analog computers. But let me say again, what most people take analog computation to be is that analog computation essentially uses continuous as opposed to discrete or digital variables to represent or model or approximate continuous problems of interest, right? So what it is that makes something an analog computer is that it uses these continuous variables. And there are generally 3 types of analog computers. Not all of them are around anymore, but they're important to understand. So the first one is the mechanical computer. This is an example of a mechanical multiplier. This is again taken from a video from, I believe, the 1950s. And what we have here are 2 inputs. We have A and B, and then an output. And we'll see how this works by kind of looking at the pieces. The input A has in this middle this pin that stays stationary. So as the input A goes up and down, it drives this lever. Now the input B has a pin connected to that piece, that part of A, with a sliding pin. So as A moves, that pin slides depending on where B is. That pin can slide back and forth. And then that pin, that sliding pin, drives the output that's on the left. And so you can see as A moves up and down, that moves the sliding pin, which drives the output. So it takes a little bit of getting used to kind of see how this works, but it makes sense. And now when those 2 pins are lined up perfectly, that is when A and B are both at the 0 point, which will make sense in a moment if we add some numbers to show the other values for the inputs. So this isn't great resolution, but you can see on the right we have A that goes up positive, down negative, B positive to the right, and to the left is negative. And so now as we input numbers, we get the result of multiplying them on the output. So when A is 2 and B is 3, we have an output of 6. And then we can just put in different values for the inputs to get kind of a feel for how this mechanical multiplier works. So again, when A is 4 and B is 4, the output is 16. And when B is 0, well, when either of the inputs is 0, it doesn't matter what the other input is, the output is going to be 0. And then it works for negative numbers as well. I think we'll get one example of a negative. Yeah, so when A is -3, B is +4, we have an output of -12. Now, this kind of mechanical analog computer is not in use very much at all, but it was one component of the mechanical analog computers that were once quite important. Another example is a mechanical integrator. So the example that I'll use here is just if we have some function in the black line and we want to compute the area under the curve, which is the gray area, we can use a mechanical integrator to do that. And the way this works, the labels are going to be, we don't really need to worry about the labels there for the particular application in this training video. But the way this works is we have the bottom turntable is our independent variable, in this case time. And then the input is this sliding apparatus that has 2 steel ball bearings that are in contact with the turntable. And then those 2 steel ball bearings drive the upper roller, which is labeled rate change here. So once that turntable starts, which runs at a constant rate, the number of rotations of the upper roller will depend on how close or far the steel ball bearings are to the center. When they're exactly at the center, that roller won't move at all. When they're closer to the edge, they'll roll faster. And so that the left and right movement of that apparatus is basically tracing the function that we want to integrate. And so the more that the rollers roll, the more area that we're calculating under the curve. And if we put a lot of those together, this was the differential analyzer that Vannevar Bush developed in 1931. What we have here is a picture of him with this differential analyzer. It's basic, in essence, it's a whole bunch of those things connected together in a sort of complicated way, but that's the basic idea. Now, one thing that people think of, if they think of anything at all, if they know about analog computers, is the electronic integrator. That might be the most familiar to people who know about analog computation. And we start with a problem. This is just for purposes of illustration. What we have here is a basic spring mass system where we have this mass M, and it's connected to a wall by the spring labeled here with some spring constant K. And we want to know how M moves back and forth. This is the X variable. When we apply some force to the side, but then we also are going to make this not totally trivial by adding in some friction, this variable B. And for this purpose of illustration, we can just set up a differential equation with initial conditions that perfectly describes this system that's given here. And then what we can do is turn those equations into a circuit. And we don't need to go into the details of this, but this is a circuit that will, the kind of thing that you would program into an analog computer and then run it. And then it would show that what happens is this thing moves, and then it goes back, and then it goes back to equilibrium, right? So those things are all very standard, and this is an example of a particular analog computer. Basically, we put a lot of those analog circuits together in such a way that we can reconfigure them. We get an analog computer of the kind that people are, like I said, familiar with. And this is just an image of a programmer actually doing a test run. And if you look very carefully, you can see she's actually doing something very similar to the diagram I just showed. Okay, so those are all fairly familiar, and none of that really challenges what I said in the beginning, this received view of analog computers where what makes them analog is that they're continuous. But that wasn't always the case, and this is what some people are not so familiar with. So this is a great quotation from an analog computer textbook that I found, where he says, 99 and 44/100ths% of the time, when an engineer speaks of an analog computer, he's referring to an electronic differential analyzer, the kind of thing we just saw. But the EDA is just one type of analog computer, one specific application of the general principle of computation by analogy. So let's see, first of all, what is meant by analogy and how we use analogs in computation. in the general sense, not just in the EDA. So let's talk about that a little bit. First, if you look carefully at some analog textbooks, you'll find that nearly all of them have some treatment of what they call discontinuous functions, right? So you can put these together in various ways so that you have functions that have discontinuities. So this is an absolute value function, what they call the bang-bang function here, a soft limiter here, a zero limiting function here. And the point is they, in one sense, weren't completely continuous. So each one has a discontinuity at certain points. So the interesting thing that you can do with those, if you put a bunch of them together, is solve problems where they're a little bit different than what we just saw. So the example I just gave with the electronic differential analyzer, we started with a well-defined mathematical problem of the kind that you'd find in a differential equations textbook. But what happens when you have some phenomenon that you'd like to study, but you do not know what the mathematical characterization is? You don't know the equations. I mean, there are various things that you could do. You could try to come up with some equations, but one of the things that analog computer programmers did was quite simple. So here's another quotation. This kind of behavior presents almost insurmountable obstacles to purely mathematical investigation, but poses no particular difficulty to analog computer investigation. Again, we're not solving equations, we're modeling systems. Thus, if we can describe the input-output relationship, all we need to do is provide an element on the computer which has the same relationship between its input and output voltages. And these elements are known as arbitrary function generators. So again, we go to our arbitrary function where we don't know how to characterize it mathematically, but what we can do is use a set of piecewise linear approximations. And different kinds of components would have different settings so that you could use more points. You could change, again, how many points, how the points are spaced. But the point is, you're approximating a continuous function with a discontinuous function, which is a little surprising to some people who think of analog computers as only being continuous. Now, there's an important caveat to everything I just said. There is a way in which mathematically, strictly speaking, these kinds of functions are continuous. They have points at which they're not differentiable. So these points here, they're not differentiable. But on a very strict mathematical notion of continuity, they're still continuous. The rough idea is if you were to draw this function, you don't need to lift your pen or pencil off the paper. Analog computer engineers referred to these as discontinuous functions anyway, but the mathematician might say, well, those aren't strictly speaking discontinuous. But there were, strictly speaking, discontinuous functions that were generated as part of analog computation practice. So this is a nice example from an electromechanical analog computer. And what we have here, there's a circuit over here. We have a variable with different points at which there are contacts. And here we have a rotating element. This is going to rotate counterclockwise. And as it makes contact with these individual pieces, then it will complete the circuit and generate some output. But importantly, there are breaks at these points. So the result is, depending on how we set up these different contacts and where those contacts make contact with this resistor, we can generate a true step function that has true steps. So this little animation will show as this moves counterclockwise what the output will actually be. See, so we have an actual step function where there are true discontinuities, right? So you might wonder, why not just approximate a step function like that with continuous functions? After all, that's something that we know how to do fairly well. Mathematicians have studied this to some, well, they know a lot about how to do this. So as just one simple example, here we have just a very basic step function that goes between two values in the same interval. And we can approximate this very simply with just a sum of sines and cosines, right? So for any particular step function, we can approximate it continuously. And there are other methods to do this too. But the problem is, as this other analog textbook states, for the problem being studied, like I said, it's not immediately obvious why the relay or the actual switch that I showed you is needed. The voltage from a continuous circuit can be made to closely approximate a step function. But there are two reasons why this is not practical. The slope of that step function out of the circuit is not exactly zero after the original discontinuity. So in the process of adding two of these step functions, for example, a small error that increases with time would be applied to, say, an integrator or something else downstream in the computer and cause an unwanted drift in the output of the integrator. So again, we have these errors here, right, which are not that big of a deal. But if these are being summed and then sent somewhere else, that can end up being really important, especially when we can just use a step function. We don't need to approximate the step function with a continuous function. We can just use a pure step function, right? So this all causes problems for the view that analog computation necessarily uses continuous as opposed to discrete or digital variables to represent or model or approximate continuous problems of interest, because there were important discontinuities. So I say we need to reject this received view and instead rely on a different view where analog computation is computation involving analog representation. That might sound circular, except we need an explanation of what analog representation is. And this is something I've worked on in the past, and there's another philosopher, David Lewis, who I base this account on, where what's important about analog representation is its representation in which the quantity that's being represented varies monotonically with the physical property that's actually doing the representing. That sounds like a mouthful, but the basic idea is it's not continuity that was the essential feature of analog computers or analog representation. A lot of times, most of the time, they were continuous, but that's not the essential feature. Instead, the essential feature is this covariation. So let me give some examples of just what I mean in more simple cases of analog representation. Here we have on the left an analog clock, and in the middle we have a record player, and on the right we have a mercury thermometer. And these are all cases of analog representation. And especially the analog clock, I think, shows the essential point that why it's an analog clock is that time is being represented by the angle of the hands. So just focus on the second hand, the red hand, for a moment. As the angle increases, the time in seconds being represented increases. And importantly, if this moves smoothly, continuously, it's an analog clock. But if it moves in ticks or in discrete steps, it's still analog because the relationship still holds. In the case of a record player, why is that an analog representation? Well, the grooves in the record they vary monotonically with the sound, the frequency, and the amplitude. And then in the case of the thermometer, this one's very simple. Basically, as the temperature increases, so does the height of the liquid, right? And in these two cases, in the case of the record player and the thermometer, you might worry, well, is it really continuous? Is it really discrete at some level? And my contention is it doesn't matter. What matters is that there's this monotonic covariation between the representation and what it's representing. So that's the view. Basically, continuity doesn't matter. What matters is this covariation relationship. Okay, so who cares? Well, like I said, I think this is a positive step toward better understanding analog computation, which, at least in philosophy, has been largely neglected. And also in computer science to some extent. I mean, people don't study analog computers very much anymore. And there's this common idea that basically all analog computers ever were these differential analyzers. So they were just continuous. But if you look a little bit more carefully at the history, they're not. And so you need a little bit more to understand what analog computers are. And also, I think this is a positive step toward understanding computation more generally. Because if it's true that there are these different types of computation, there's analog computation, digital computation, etc., then we need an account of computation in general that explains why all these different things are the same kind of thing, right? Why are they all computation? What unifies them in some general sense? And also, I think this helps us get a grip on how certain neural processes in the brain might literally be computational. We don't need a kind of separate sui generis account of computation to apply to neural systems. If we really understand analog computation, then I think a lot of what computational neuroscientists are talking about when they say the brain computes is they're actually talking about analog computation. And especially when we don't tie analog computation to the idea that analog computation must necessarily be continuous. Instead, if it's just a monotonic covariation between a representation and what it's representing, that might make sense of a lot of analog computation. And that's actually what I'm writing a book on right now. Okay, so that's the end of my talk. Thanks very much. Here's my email address and website if you would like to contact me. I would love to hear from people. And I think now we'll turn it over to some discussion.
Yes, Corey, thank you very much for your interesting lecture. And well, not much discussion because I'm just here alone. But anyway, the question which it bothers, I think, me and everyone, and it still will bother lots of people for the good time, is that I think we tend to think that computation is very much digital.
Yes.
That's when you say compute in, I think most of the people, I mean, scientists or even the people from out of science, they will think about digital computation. This is what is around us. Yeah. So when you say analog computation, I think there's a very deep and profound misunderstanding and confusion. Because for me, analog computation is something is going in and something is going out. It's just the system is responding right away to the input and gives you the output. In the case of digital computation, you need the algorithm, you need all the stuff to run those function and equations and so on. So I think this is very much confusing. And when you speak about brain and that the brain is computing, then I think most of the people, I have to just increase the volume of, most of the people, I think at least I am confused because I don't think that my brain is computing. I know there are a bunch of books and people say, hey, the universe is computing. But then if I just throw the rock, which is falling from the whatever place down, then this sure we can using physics we can calculate the trajectory of this rock. But then if I say, well, this falling rock is computing its trajectory,
right?
It sounds completely nuts. I mean, this is insane to say something like that. But that
I agree.
But somehow I think the trajectory of this rock falling down from the airplane is very similar what this analog computation does. It just responds to the input and gives you the output, and it's not calculating anything on this trajectory from the start to the end. It just goes according to whatever trajectory, and that is the essence of for myself, the analog computing. That you don't care about those small increases of time or whatever. You have input and output. And if you look on the classical physics, how it is formulated, you have exactly, this is what I'm saying. You have the conditions, initial conditions, and then you have the end of the story, and in between, everybody knows what's happening in between. It's just the result, and it's just going whatever way it's going. But if you look on this question or this problem from the digital point of view, then at the very point of this trajectory, you have to make calculations to know what will be the next. Because your algorithm has to go in steps, okay? Increase the distance or the time, and then every time you have to do calculation. This is not the case. This is, as I think, this is not the case with the analog computation. You just, and with physics, it's just, you just throw the rock and it's here and there, and then you know this is whatever trajectory. There's no calculations of the next position during the movement of this rock. And this is very similar as in an analog situation, and this is completely different than in the digital situation. This is also, I'm sorry, this is also very similar to these artificial networks. When you have, it's very, very similar to what the analog system work. That when you have input, output, and you have those layers in between which adjust their weights, and then you have the result. And this is not the digital thing, although you can run this on a digital computer.
Sure, you can simulate them. Okay, so yeah, a few things. First, I totally agree with this idea that it's ridiculous to say that anything or everything is computing. Philosophers call this pan-computationalism, and it trivializes the view that there are computers, because then it means everything's a computer, so you will not find anything that is not a computer. So then it's completely uninteresting to say, oh, well, the brain's a computer. Well, of course it is, because everything's a computer. And I agree with that. I think any view of computation that counts literally everything as a computer is not restrictive enough. I think there are some facts that matter about what things are computers and what things aren't. So the view that you mentioned is very much entrenched. You're right. What people take computing to be is digital computing. What I would say to that is, yeah, the success of digital computation is, undeniable. But there were several decades where what people meant by computing was analog computation. There was a big competition. When digital computers first came on the scene, most people didn't think that they were very useful because they were way too slow compared to analog computers. And so if you take the view that you mentioned seriously, that what computers are is only digital computers, then we have to seriously revise this idea that people were using computers before there were digital computers. I mean, if you look at, I have all of these stacks of textbooks, like electronic analog computers. I don't know if you can see it.
Yeah, I can see it.
50s, right? And this is before there were digital computers of any, real sense. And so all of these people called these things computers, and I think they had a principled reason to call them computers, because they were solving computational problems. And unlike just a natural system where you're throwing a rock, yeah, you can describe the dynamics physically. And in a sense, they're similar to analog computers in that you give it an input and then an output comes out. But I think the difference is with computers is you have some kind of representation. And not everything, I think, is a representation. So that was, part of the point that I'm trying to make, is that analog computers had these internal representations. And that's what makes them similar to digital computers. Digital computers also have a representation. It's a very different kind of representation, but it does act on those representations internally. So it's not just an input to an output and just a flat mapping, but it's an input that acts on representations in some ways and then produces an output. And those representations are what make it a computer. And I think that's what neuroscientists have in mind when they say that the brain computes. It's not just that there's an input and then an output. I mean, if all you're worried about is input and output, as you know, that's very cheap. You can characterize that however you want. But having a representation that's an intermediary between the input and the output, where it represents something in the world or something of interest, right? That's very different. That's not easy to get. And I think that's what people were doing with analog computers. Well, I mean, that's very much what they say they were doing with analog computers. And this is tricky because a lot of people think, for example, that Turing sort of defined computation for us, right? And he came up with this notion, or at least the early versions of digital computation. And then John von Neumann designed the machines that use digital representation to do digital computers. But the point that I want to make is about that is that the notion of computation, I mean, as people who understand Turing know, he was building on one particular notion of what humans do on pencil and paper, right? But there were other notions of computation, like people using, say, early versions of slide rules. Those people were doing computations also. And so analog computations, in a way, are the sort of mechanical versions of what people were doing with slide rules in some instances. The digital computations are the mechanical versions of what people were doing with, pencil and paper and numerals, right? So although it is true that when most people think, and I have some great quotations from some computer scientists in the 70s when they were involved in these debates about whether analog computers are better than digital computers or vice versa, when they start saying, we can't forget that computation means analog computers too. When digital computers became fast enough, then there was no reason to use the analog computers anymore because analog computers have limits on their precision, whereas digital computers, you can have as much precision as you want, as you know. And so once digital computers became fast enough, then analog computers just, no one used them anymore. There was no reason to. But still, if you, like I said, if you insist that computation means digital computation with digital algorithms, then you have to say all that stuff for the previous decades when people were doing analog computation, they weren't really doing computation. They were all confused. They were doing something different. And I think that's a very high burden of proof to say, no, you were all confused about computation. And when you said, oh, well, there's these two kinds of computation, there's analog computation and digital computation, and they're in competition, you weren't even talking about computation. You were talking about something else and computation. And even to make sense of those debates and to make sense of what they were doing, we have to say that was some kind of computation. It's different than digital computation, but it's still generally the same. And I mean, that's because so few people even care about analog computation these days. It's not obvious exactly how to characterize what does make them the same kind of thing. But like I said, my view is that there are digital representations, there are analog representations, and there might even be other kinds of representations, I'm not sure. But what makes something a computer is that it has some mechanism that does something with those representations. So, I mean, that's what I would say to that. Mm-hmm. But I do agree. Any view that says if you throw a rock and it's computing, that's ridiculous.
Yeah, but people tend to think so, but anyway, the point is, and my thinking is also very simple, that in the case of the analog computer or computation, you need very little energy to do the work. But in the case of digital computers and computing, you need lots of energy. And if you think about small hydrogen atom, or even a little bit more complicated, you have to have this big, huge digital machine, running whatever big algorithm to get some kind of picture or understanding how this tiny hydrogen atom is working.
Right.
And then if you apply quantum mechanics to this hydrogen, well, the solution in the case of the hydrogen atom, the exact solution in quantum mechanical solution. But if you just go a little bit more complicated, then using the digital approach, you have to run those big machines for many hours to get this very small, atom or two hydrogen atoms, or a few hydrogen atoms to understand what is going on there. Yeah. And when you think about this, I mean, come on, is this possible that the God designed this world in such a crazy way that, you need a big box, and it's in liquid nitrogen, not, I mean, but if you think just for a moment about analog I don't know how to do this kind of, how to find a solution using the analog approach to this, let's say, quantum mechanical or whatever, those small few atoms problems. But I strongly believe that one day we will just have the, input and output, and this is how the nature is doing, how this is how it's working. And then when I heard about your book, and my thinking was that you will just go in such a way that you will try to prove that, well, digital thing is too precise, too exact. In when you when you observe nature and whatever small quantum mechanical phenomena in nature, then you will right away find out that this is much more simple than that the digital thing is able to describe. It's just in and out, and it's working. For example, think about photosynthesis. Okay, this process is continuously going on this planet, and you have millions and millions of molecules, and whatever processes are involved in photosynthesis, you have in and out, and it's going continuously with great speed. If you take even the smallest photosynthetic unit and try to figure out what's going on in this thing from quantum mechanical point of view and digital, then it's completely impossible. This is bloody difficult. You have those wave functions and whatever you have there. It's very, very complicated. And of course, there's lots of people who are trying to solve this. But my thinking is very much different, that somehow this analog approach, that everything is in there, you just have a photon coming in, and then you have the result. And everything is there. There's no calculations per se, as in the digital sense. It's just in and out, and everything inside is already designed in such a way that there's no need for doing differential equations, just in and out.
It just
And
does
this and this is very much like in the case of the analog systems. And when you said, I was just thinking for a second that in your book you will just try to persuade people or to show that this digital thing is great because we could not see each other and so on and so on. There's no question about that.
right.
But 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 then because everybody's in this digital thing, we have to, I think, we have to sometimes to understand that this is the end. The end is coming very soon, because when I'm old enough, and I remember the very past, and it was always when you bought the machine, then after a few months you wanted the bigger machine because it wasn't enough memory or whatever speed. After you got the next machine, which was bigger, faster, and so on. And then after a few months, you wanted even bigger machine, and it's endless. But at the same time, and this analog thing and all the nature around us is doing whatever it's doing, and it's just working. I know this is a primitive thinking that nature is a teacher to us, but in a way, it's just, I think there's something in there. And I think it was Feynman who was saying that he cannot, well, I have to search for his quotation, that he was saying something like about that he could not understand why the atoms or whatever small systems could be digital and consuming so much energy, to calculate whatever is going on there.
Yeah, exactly. And I mean, I think that this illustrates a point that I made just very briefly, but the kinds of things you're talking about when we do these very complex simulations, these digital simulations of very simple systems, and it takes, literally trillions and trillions and trillions of these calculations to figure out what these tiny things are doing. It would be ridiculous to say, well, because we've predicted what they're doing using these trillions and trillions and trillions of digital computations, that's what the thing is doing too. Like, no way, not at all, not at all. It's just doing whatever it's doing, right? Yeah, I totally agree with that. And one thing, I was thinking a little bit about your comment that analog systems are just kind of input and output. One example that I think most people would never think of this as an analog representation or an analog computation at all, but it's it's one of my favorite examples. Well, first of all, you know about tree rings, right? Tree rings are a way to, if you want to use them as a representation of time, you can, right? You cut down the tree and you can figure out, okay, so we count the rings. The more rings there are, the older the tree is, right? But the tree is not using that as a representation at all. The tree is just doing what it's doing, right? But interestingly, there are these insects, cicadas, some people call them locusts, and a very interesting thing about them is they're a slightly different species, and they spend most of their life underground. But they come up, they live in them under the ground for years and years. They come up, they're alive for about a few weeks, and then they die. Right? They come out of the ground, fly around, mate, and then they die. Biologists have realized that the different species, the number of years that they come up out of the ground are prime numbers. So there's some that come up out of the ground after 13 years, some that come up every 17 years, right? And it was an interesting kind of question, like, why are they these prime numbers? But then they figured out if they're prime numbers, that reduces the number of times that there will be any overlap, that the species will come out of the ground and compete. But then the question is, how do they know how many years it's been? And it turns out it's a kind of analog representation. There's a little like counter basically that just adds one every year. And when it gets to the right length, the system knows, okay, it's this long, which means 13 years. So now it's time to come out of the ground. And so that's a kind of, to me, an interesting example of, it's not digital because it's not representing the digits of the numbers like a digital computer. It is just the longer that, I think it's a protein construction is, there's like a piece added for every year. The longer that is, the longer it's been underground, and when it reaches a certain limit, it's like a simple counter and it comes out of the ground. So that's a kind of, strange example that people haven't heard of, but it's a kind of very basic analog computation, because unlike the tree that just happens to be, counting these years going by as it's adding tree rings, the cicada is actually using that counting to do something for it. And so I would call that an actual representation. Unlike these, other systems where they might be doing something that we could say is described by, various differential equations or whatever, but it's not, the system isn't representing anything. It's just doing what it's doing. So I just want to throw that out there. That's kind of an interesting example of a kind of analog representation. It's not immediate input-output. It has kind of a long, multi-year memory for these things. And I wanted to make another point, but now I forgot what it was. But I do agree with you about this idea that, it's a separate issue, but we are coming up on hard limits to how fast we can do things with digital computers. And this is a little bit outside my area of expertise, but I would be interested in what kinds of things people could do if we started developing analog computers again, because the technology is very old. A few people are doing this, but in some cases it can be much, much faster. And so one example that I like to use, this isn't my own example, but if you want to find the largest number, say I give you a stack of cards, of say, 500 cards, and on each card is written a number in digital format. Let's say it's a 3-digit number. And I say, find the largest one. You have to go through all 500 cards, and then, you have to remember which one's the largest so far. And after you've gone through all of them, you'll have the largest one, right? So the number of steps is the number of inputs, right? But if you have the numbers represented in an analog format, like if you have uncooked pasta, right? So uncooked spaghetti, where the length of the noodle in millimeters is the number that you're representing, and you have 500 of them, and you want to find the largest one, well, you just kind of hold them loosely in your hand and go like that, and the top one's right there, right?
That's what Italians do every day.
Exactly. And so, that only works within a certain precision. If they're all very, very close, it's going to be hard to do. But, it's a one-step process. So, if you have 1,000 or if you have 10,000, as long as you can get your hands around it, you can find the largest one in a single step, right? Unlike, as you mentioned, the digital way of doing it, the more inputs you have, the more energy, the more steps, the more you have to keep track of, et cetera. And that's one of the benefits of analog computation that I think people have lost, because now the digital computers are just so fast, we can largely get around that problem. But, when we're looking at, simple systems or biological systems, maybe they evolved in ways that don't take up all that kind of energy and resources, right? I mean, we might think that they would evolve in ways that try to minimize the kind of resource use. So that's another reason I think we should take seriously, like, maybe nature is doing things in this analog computational way. Even though we can do it digitally, there's not a lot of reason to think that nature is doing it that way. So on that point, I think we're very much in agreement.
All right. No, this digital precision is terrible thing. I mean, this is. I know. Who cares if this is 1 minute or 2 minutes calculations computer time? I mean, there's no big deal about this. I mean, I can wait, of course, 1 minute to finish the calculations. But I'm speaking and thinking about I mean the general approach and thinking, about that. And the same. This is again the digital thing is killing itself, because in the case of this analog computation, well, sure there are errors, but everywhere, if you look around and if you think about the world around us, the errors all over the place.
Yeah.
There's no. Going back to this photosynthesis, you have photons with different energy coming at different direction to this photosynthesis. So it's very much not very precise that you have this photosynthetic unit and the photon is coming right away perpendicular to it and so on, because you may have a cloud between then. Lots of things is happening, but despite of that, all those photosynthetic units, they work because there's plenty of them. They do work. And this is like in the analog system. You can put 10,000 units to integrate the input. And even if you have errors, as on your slides, you have this, approximation of the step function. Of course, you have errors, but who cares about those errors? I mean, in the sense that overall result is just fine.
Right.
I remember when I was a student, we got the pocket calculators, and there was a 5-point, and if it was cheap calculator, you have the 5 digits, and if it was more expensive Japanese, there was 20 digits. So everybody was writing 5.678, and then the teacher was saying, "Come on, boys! I mean, think about a little bit. What is the meaning of this? What's the meaning of this?" And precisely we are in the way going for precision, but this precision is killing the whole thing, and we are lost in the precision, because tomorrow weather will be the same like today. I have 50% without any calculations, that the weather here will be in the same in your place will be 50% like today, and the next day maybe will be 40. I'm not doing any calculations, and I'm doing so anyway.
Yeah.
Okay, I like this. I like this. Your comment about the no equations needed to look at the thing, and this is again the question. It's like going back to this photosynthetic unit. Sure, we can write. We have quantum mechanics, and there are lots of people who are working on this because it's a very important issue. And you have plenty of equations and so on. But my feeling is that you don't need all of those equations. And this photosynthetic unit does not care about those equations and quantum mechanics and interpretation of quantum and so on. You have just something at the beginning, something at the end. And the nature is not interested in the function, per se function, which is connecting the input and output.
Right.
I don't know how to. I have no precise thinking about that, but that is my kind of general notion that it must be much more simple than it is in the case of digital thing, and the hope is with the analog approach.
Yeah. Let me go back to something you said about the precision. this is, I think, an important point in thinking about, one of the things I'm interested in is, whether neurons can compute. And one of the really interesting things about the digital versus analog approach to the introduction of errors, or like perturbation, if you have, very simple digital representation, like you said, like on a calculator, right? You have, say, 523.12, right? So it's representing all of those digits. And how bad the error will be depends on which of those digits you perturb, right? So if something happens and, the 0.12 gets altered a little bit and it turns into 0.13, no big deal. But if one of the most significant digits gets perturbed, the 500 and whatever turns to 600, then you've got a huge error, right? And that doesn't happen with analog systems, right? There's not that kind of what's the most significant digit, what's the least significant digit. A little bit of perturbation is a little bit of perturbation, right? And it seems like, in systems like brains, there's noise all over the place. And if it were digital, that would be a disaster, right? You mess up the right single bit in your digital program.
That's it, over.
Yeah, right. But if it's not representing the digits, it's just, the voltages are,
Precisely.
yeah, then it can handle error in a way that, people want, and you really want in a natural system. I think that's a really good point. And that's something that we forget about the actual, how digital systems actually work. And it's, computer engineers have to worry about this a lot. So I just want to go back to that point. I think that's exactly right. I totally agree with that. But
that was hope with this neural networks that you can go easy with the precision and still get quite nice results. I recall at the end of 80s, and 90s, but that was a great hope that networks will kill and to find a solution for every possible problem. But well, there was quite a success, but I think it was limited, and maybe the analog approach is the next interesting step. I don't know.
Yeah, I don't know either. I mean,
this is also the question about mathematics. It's the question about representation, precisely, that we tend to think, because this is our background, education background. I mean, you think like everybody thinks in the West in the such a way that we went through the same schooling system, though in different languages, but the system is precisely the same. 1 + 1 gives you 2. And then you tend to think that 1 or 2 exists somewhere, like in Platon philosophy.
Yeah.
But then there is a question of representation. And if you go, I don't know how familiar you are with the philosophy of mathematics, but I just spent recently good time of reading, and this is completely science fiction. I mean, those guys in mathematics, they can say everything they want, and they cannot prove it, because, I mean, how you can do it? In the case of physics, let's say, you can do whatever experiments, and then, but in the case of mathematics, and then what I'm trying to say here now is that, sure, you are aware about nominalistic interpretation of mathematics, and there was a few approaches done, some 20, 30 years ago, and that was a hope to change mathematics from this digital, I mean, 1, 2, 3, 4, 5, to the relationship that exists between 2 and 1. Right. And that was also a very interesting approach, which is never kind of got a good recognition, this nominalism in mathematics, but that was also a way to get rid of this all the traditional thinking about digits, and that the digits, they do represent something. It was just new thinking that there's a relationship between apple and something else.
Yeah.
Also, the category theory in mathematics is very interesting from our point of view of our discussion, that you have categories, and then you have relationship between different categories which describe the system. That then you don't So finally, you use mathematics, but this is just at the end. First, you think in the terms of categories and the relationship between units of your system. Right. And then, sure, for convenience, you can digitize this and put into numbers, but the thinking is completely different. You don't think about 1, 2, 3, 4. You think about category good guys, bad guys, and what is the relationship between those categories.
Yeah. Category. I've not studied much category theory, but yeah, I totally agree with the basic idea of well, I'm agnostic about how the metaphysics of mathematics works, because on the one hand, one of my teachers in grad school wrote a book about this, and on the one hand, it seems insane, this Platonic view that, numbers are out there and they're abstract objects and they're outside of space and time, but somehow we know about them. That seems crazy. But also, it's remarkable that if anything is true, it seems the truths of mathematics are true. It's not just, like convention. It seems, like the paradigm example of objective truth. And how can that be the case if there are no things that we're studying? So I'm agnostic. I'm totally torn on those sides of the debates. They both seem totally crazy to me. So, but yeah, for the purposes of computation, we don't have to worry about that so much, because all computation is about the representation of these things, and we don't need to really worry about, are they really out there, or whatever they are. Yeah, we're not really ever computing with 2. We're computing with some representation of 2, whatever that means, either the numeral 2 or 2 hash marks or whatever. Yeah, but I don't know what to say about math.
All right, Corey. Nice discussion. Sure, we can keep going, but that is just to end. I was really fascinated by reading this stuff about mathematics recently, and again, it just came to me again and again, because of course I was when I was young, I knew about this stuff, but then now I'm getting older, so it was really a shock to me to read that something. I just. But then of course, I think behind this there's a way how we think.
Yes.
And then maybe we should have 100 young babies and not to teach them mathematics. as we know, all the Romanian kids are taught in the school. Maybe they will find out some kind of different, because I mean, you or me, I cannot think of numbers. I mean, this is just impossible. It's just we are so much stuck with this that it's.
Oh, yeah. It's deeply entrenched.
This is social, because that's the education system, and we went through the same education system. And I remember it was a few years ago when I spoke to the people working in weather prediction.
Uh-huh.
And sure, they calculate the average of temperature at the given location during the summertime, whatever. They always use average temperature, let's say.
Right.
But I told them, hey guys, well, you cannot do that. Hey, revolution. But because, well, the point is that if you want to calculate the average of given function, as mathematicians they do, it has to have certain properties. So to calculate the average of something, you have to know what are you calculating. Right. I don't want, because I should write a few equations to show you. But the point is that I was kind of like, whoa, they just threw me away in a minute, because I was just questioning what they were doing every day, doing average calculation of temperature at the given location. Right. But to do this, you need to check how is your function, and is this possible to make calculations of average of this function. But nobody cares about this. And this is what I'm saying right now, is that this is the background. For them, it was just doing the average and forget. I mean, stop it. Don't. I mean, this is a normal. This is what we do every day. And the same with mathematics as we know it, and we were taught, we cannot kind of jump out of this and to have a different way of thinking. And Can you add numbers using the analog computer?
Can you add them?
Yeah.
Yeah, if you think of numbers as being represented by, say, a voltage.
Yeah, exactly.
You have
So
5 volts, 10 volts. Yeah.
So correct. Yeah, sure, of course. But then you can do whole mathematics, right? Using the analog computing.
Yep.
Let's say you open your textbook from the high school, and then you can rewrite this book. On one page you have this traditional page as it was before, and on the right side the page you have this analog thing that you have those triangles and voltages and so on. You can rewrite this.
Well, that's really tricky because it turns out writing numbers, like literally writing numbers on a page digitally, is really, really efficient. So we'd have to come up with an entirely new notation system. We wanted no digital representations at all.
No,
right?
but
So,
you need this digital representation because you want to pass the exam. And your
right.
teacher is saying, okay, Corey, you got, instead of 21, you got 25. I'm sorry, you cannot.
Right.
But if you have this analog or representation, and then you have even errors in your answers, and still they're okay.
Yeah. And for some answers, you might not have errors. This is one of the things, minor point, but, analog computer engineers spend a lot of time figuring out how to minimize errors. Yeah. Mm-hmm. So, if you need it to be 5 decimal points, then you're not going to get that. But if you need 4 or 3, you could probably get that. Yeah.
Mm-hmm. All right. Okay, Corey, when your book is ready, we'll be ready. we are waiting for this thing,
I'm working on it.
Well, the question is when you finish.
Yeah, that's a good question, but
now we have to press you on this issue because then you will just work more efficiently.
Yeah. I've got more than half of the material, so it's on its way.
Well, no, okay. So you mean that before the end of this year you will be done?
My plan is to have it done. In the fall I have to teach, and this last year I didn't have to teach at all, so I've been doing all the research for this the past year.
So you were in a sabbatical?
Well, I was on a grant to work on this stuff. So all the hard part, all the research is done. So yeah, now it's the writing. But in the fall, I have to teach completely unrelated things to this. So that's going to take some time. But this summer I'm going to work on as much as I can.
Yeah. So forget teaching, just write. Okay, Corey. We will cut out. We will cut out this end of this. So
if you want to, that's fine.
Nobody will know.
Okay.
All right, great. Thank you very much, and we will do our job, and then I will email you with the result, and then
Okay, that sounds great.
Please continue because I think this is just my general feeling is that this is the right moment to come up with what you were saying during your presentation. Right. And to point to the people. But I think to go this way as you are suggesting or thinking, or you will think, because sure you will do, it's a very much, there will be lots of opposition of people who are only thinking about digits and, this guy, he's just errors. But don't worry, you are young, so you have next 50 years to keep going on the subject before they will try to kill you.
I'm glad I look young. I'm not that young, but thank you.
Anyway, yeah, because I think that if you go to those people with this class, everybody has classical education, come on.
Yeah.
But what? No numbers? There is a book. I will send you a copy of this book. Mathematics Without Numbers.
Oh, Hartshfield?
Yeah.
I know this. Yeah.
And there was okay. Anyway, when you just read this, what the hell is that? This guy must be drunk or something. Well, no numbers. How can you do anything without numbers?
Right.
But he was making lots of points, and I was having a nice discussion over the internet with him recently.
Yeah.
He is doing just a little bit different stuff right now, but that was I think that was because he could not handle this. He was alone, and everybody was drifting to the right, and you just go to the left. And then suddenly, after a few years, you're sitting in your room at the university. Nobody's coming, nobody's knocking, nobody's calling. I mean, if you write the paper, there's just those reviewers. They just give you a shit, that you are crazy nuts and wasting public money by just doing. I mean, so you need lots of energy to do that.
Yeah. I'm
never give up.
the opposition.
All right.
But thanks for the encouragement.
Yeah, I will push you every day.
All
Okay,
right.
so take care and see you next time in whatever place.
Okay. Thanks very much.
Thank you. Take care. Bye-bye.